Hello viewers, I am Dr. Mala Das Sharma, retired professor of St. Pius X Degree and PG College for Women, Hyderabad. You are watching my channel Chemphilic. So let's start the 22nd episode of Teaching Chemistry through Riddle. Watch the video till the end and enjoy the complete riddle and also join me in the question answer session. So, this is our riddle number 22. X is a phenomenon related to an identification technique of organic compounds. This identification technique gives a pattern where the absorption position of different protons present in a compound are found. The shifting of the absorption position of protons with respect to the standard reference compound is different as the protons present in the different environment of the molecule experience different magnetic field. The shift may be upwards or downwards direction with respect to the chosen standard. So this is riddle number 22. Now let's see the questions. The primary question or first question is, what is X? The answer is chemical shift. Second part of the primary question is, name the identification technique referred here. Answer is proton NMR. Now let's see the other questions related to this riddle. Second question, why the absorption position of the protons gets shifted? Third question, name the reference compound mentioned here. Fourth question, under what situations upwards and downward shift occur? Now, this riddle is framed to explain the principle of nuclear magnetic resonance spectroscopy. In part 1, already I have discussed a part of the principle, and now in this part 2, we will discuss shielding, deshielding and chemical shift in NMR spectroscopy. Now, in part 1, what we have observed that, what I told that, nuclei of some isotopes have mechanical spin. And these spinning nucleus, they generate a magnetic field. So, the spinning nuclei, they act as tiny bar magnet. Now, in absence of any external magnetic field, this magnetic moment of this tiny bar magnet orient at any random direction. But as soon as the external magnetic field is applied, then this nucleus or this magnetic nucleus, they take some specific number of orientation, which depends on the nuclear spin number. And we have seen if the nuclear spin number I is equal to half, then two orientations are possible. One orientation is that where that direction of the magnetic moment of this magnetic nuclei is parallel to this external magnetic field, and another orientation is the direction is opposite or anti-parallel to the applied magnetic field. So, in presence of the external magnetic field, this nuclei can take any one of this orientation, and in the orientation where this direction of the magnetic moment is parallel to the external magnetic field, that is the lower energy state or lower spin state of the nucleus. And in another orientation where this direction of this magnetic moment is opposite to the applied magnetic field, that is the higher energy state or higher spin state. Lower energy state we denote it as alpha, higher energy state as beta. And in nuclear magnetic resonance spectroscopy, we pass radio waves and we keep the radio frequency constant. And this external magnetic field is varied. So, at a certain external magnetic field, this frequency of the radio waves becomes equal to the precessional frequency of the nucleus, or the energy of the radio waves is equal to the energy difference between the two spin states of the nucleus. And when this occurs, this situation is called resonance. And when this occurs, then nucleus flip from the lower spin state to higher spin state. That means the lower energy state to higher energy state. This transition occurs, which is known as the flipping, and we will get the absorption spectrum. Okay, this part I'll explain in part 1. Now, see, the nuclei is spinning, and we have also discussed in part 1 the precessional motion and everything. And now what happened? This electron in the surrounding nucleus, or specifically the electrons at the chemical bond, they also start a circular movement, or they start circulating in presence of the applied magnetic field, and they start circulating at a perpendicular direction with respect to the applied magnetic field. And as these nearby electrons of the nearby nuclei are circulating, then another magnetic field, which is known as the secondary magnetic field or induced magnetic field, is generated. Let's see. So, under the influence of applied magnetic field, electrons surrounding a nucleus start to circulate perpendicular to the applied magnetic field, H0. So, they generate a secondary magnetic field called induced magnetic field. Now, so this induced magnetic field, which is generated by the circulation of the electrons of the nearby nuclei, or specifically that circulation of the electrons at the chemical bond. Okay, this induced magnetic field, it reinforces the applied magnetic field in some location or some region. See, here this region where you are observing the magnetic lines of force, here it reinforces the applied magnetic field, and in some location or some region it just opposes the applied magnetic field. Let's see. Circulation of electrons about nearby nuclei generates an induced magnetic field that can either oppose or reinforce the applied magnetic field at the proton depending on its location in the induced magnetic field. Now see, if the proton is in this region, which region? Where this induced magnetic field reinforces the applied magnetic field, then we call it as the proton is in deshielded region. Okay? And if the proton is in this region where this induced magnetic field opposes the applied magnetic field, then the proton is said to be in the shielded region. Okay? Now, in the deshielded region, this proton is experiencing more magnetic field, and in the shielded region, proton is experiencing less magnetic field. Let's see. If the induced field opposes the applied field in the region of proton, then the proton is shielded. If the induced field reinforces the applied field, then the field experienced by the proton is greater than the applied field. Such proton is said to be deshielded, and this effect is termed as deshielding effect. Now, what I told, if the proton is in the deshielded region, then it is experiencing more magnetic field. So when it is already experiencing more magnetic field, then it will flip. That means that nucleus will flip at lower magnetic field, means lower external magnetic field. Okay? And if the proton is in the deshielded region, then it is experiencing less magnetic field, because this induced magnetic field opposes the applied magnetic field. Then for the flipping of the nucleus from the lower energy state to higher energy state, then it requires more magnetic field. That means flipping occurs at more external magnetic field. So deshielded proton absorbs at lower magnetic field and shielded protons absorbs at higher magnetic field. And this shift of this absorption position of this proton due to its placement at the deshielded or shielded position, that is known as the chemical shift. Let's see. Compared to the naked proton, shielded proton requires a higher applied field strength, whereas deshielded proton requires a lower field strength for transition. Thus, shielding shifts the absorption position upfield, that means higher magnetic field, whereas deshielding shifts the absorption position downfield, and these effects are termed as shielding and deshielding effect. So, such shifts in NMR absorption are called chemical shift, as they arise from the circulation of electrons in the chemical bonds. Now, what is this chemical shift? This chemical shift is the difference of the position, means absorption position of a reference compound. Here we take the reference compound tetramethylsilane or TMS, and the absorption position of any proton which is present in a particular location of the molecule. Just imagine here is one absorption peak of one proton, and then this difference from here to here, that is the chemical shift of that proton. Okay. Now, chemical shift we express in Hertz, and we consider the chemical shift of TMS is 0 Hertz. Okay. And this TMS position is extremely right. As you are coming left hand side direction, that indicates the downfield, and this chemical shift we express in terms of delta, and delta value increases in the left hand side. That means this chemical shift is in the left hand side. This indicates the downfield, that means lower magnetic field. Okay, so delta value more means it is downfield. Chemical shift is in downfield, and delta value less means chemical shift is in upfield. Let's see. Chemical shift is the difference between the absorption position of a particular proton and the absorption position of a reference proton TMS, that is tetramethylsilane. Already I explained. Now, we can express chemical shift in terms of Hertz by setting the TMS peak at 0 Hertz at the right hand edge. Here. The magnetic field decreases towards left. In this direction, it is downfield. Magnetic field decreases. The chemical shifts are commonly expressed in delta unit, which is a proportionality and thus dimensionless. Delta value increases in downfield. Now, let's see the answers of the remaining question. Second question was, why the absorption position of the protons gets shifted? So already we have discussed that electrons of the nearby nuclei or electrons at the chemical bond starts circulating in presence of the external magnetic field. Circulation of this electron generates another magnetic field or induced magnetic field or secondary magnetic field. Okay, and this secondary magnetic field, it reinforces the applied magnetic field in some location of the molecule or some location where protons are present, and in some region or location it opposes the applied magnetic field, where this induced magnetic field reinforces the applied magnetic field. Then those protons, that means protons which are present in that location, they experience more magnetic field, so their absorption position shift at the less magnetic field. Okay? That means less magnetic field required for the transition. And the protons which are present at the shielded region, that means where the induced field opposes the applied magnetic field, then those protons, that means protons present in those areas, they experience less magnetic field, so their absorption occurs at higher magnetic field. That means the position of the absorption peak shifted. So this already I have discussed, already I have told now, that is only written here. Now, third question. Name the reference compound mentioned here, that is tetramethylsilane. Now, fourth question. Under what situations upwards and downward shift occurs? Now, compared to the naked proton, shielded proton requires a higher applied field strength, whereas deshielded proton requires a lower field strength for transition. Thus, shielding shifts the absorption position upfield, whereas deshielding shifts the absorption position downfield, and these effects are termed as shielding and deshielding effects. So this is our riddle number 22. Now let's see the viewer's question associated with this riddle. So today's question for the viewers: two types of protons are present in an organic compound, A protons and B protons. From the NMR spectral pattern given below, I'll show it, identify the deshielded protons. So NMR pattern is this one. This is A proton. This is the peak for B proton. You have to identify the deshielded protons, whether it is A protons or B protons. Now, mail your answer to malakemphilic@gmail.com. You have to write your name, then your affiliation and place. Then you have to write answer of the viewer's question of the riddle number 22. Then write your answer and send it at your earliest. Time to time, I announce the names of the viewers who will give the correct answer. Join me in this program and encourage me. Thank you.